Hello, everybody. Welcome to today's lecture. So today we're going to finish up chapter 9. Um, I, I think I said initially we might need 3 lectures for it, but I was looking back through it, and this section's actually very short. And then there's only 2 more sections, so we'll definitely finish it up today. Might be a little bit longer than normal, though. But just as a reminder of what we're doing here, we started to look at hypothesis testing, which is exactly what it sounds like. You make a hypothesis and now you need to test that hypothesis. So how do we do that? How do we write that down mathematically? And how do we look at the results mathematically? Okay. So some important things we'll need to remember going forward from last time. We have the null hypothesis, which is the statement that there's no difference between the variables we're looking at. Or we would say there's no statistically significant difference. We denote that by H naught, which is like H with a subscript of a 0 or an O. And then you have the alternative hypothesis, which is contradictory to the null hypothesis. And it's a claim about the population, and it's what we conclude when we reject H naught. Okay, and we denote that as HA. So we gather our evidence, and then we make a decision. We either reject H naught or we fail to reject H naught. So if we reject H naught, that means we're accepting the alternative hypothesis. If we're failing to reject H naught, then it doesn't necessarily mean anything. It doesn't mean that we're accepting H naught, but it means that we can't necessarily accept the alternative hypothesis either. Usually the alternative hypothesis is what we are trying to prove. Okay. And as a little tip for how we determine which is which, the HA doesn't have an equal sign in it. Okay. And then on 9.2, we just talked about the different types of errors. So we talked about the type 1 errors and the type 2 errors. Typically, type 1 errors are considered worse, but we did see an example where the type 2 error was worse. I think it was in this example right here. But typically, type 1 errors are considered to be worse. And then we had our alpha and our beta. Alpha was the probability of a type 1 error, which you might remember as the confidence level also from chapter 8. And finally, the beta is the probability of a type 2 error, and 1 minus beta is known as the power of the test. Okay. And we already know 1 minus alpha is known as the confidence level. So that's just a quick recap of everything there. So let's jump into 9.3 now. Like I said, this chapter is very short. This is just called distributions needed for hypothesis testing. Okay. So this is kind of all stuff that we've already talked about. In the last chapter, it just kind of applies here too. For let's make a chart of what we're testing and the distribution associated with it. Okay. And there's only really 2 of these, so we don't necessarily need a chart, I guess, but it's okay. So if we're testing for a population mean, okay, so if our test involves a population mean, then you might remember from chapter 8, whenever we were looking for the population mean, like if we were looking for the confidence interval containing a population mean, then we were using the normal distribution. Okay. So this is the distribution we want here, or I guess we can just write normal. Okay. If it's a population mean but we don't know the population standard deviation, then that's when we use the student's t distribution. Okay. So if we do know the population standard deviation, we use the normal. If we don't, then we use the student's t distribution. Okay. There was another one we didn't talk about. That was if we were looking for proportions or percentages, we use the binomial distribution. That was back in chapter 8. It was one of the sections that we skipped, so we'll keep skipping it here. So in general, we're going to be looking at things where we're looking for a population mean, and then we just don't know it, and maybe we'll know the population standard deviation, maybe we won't. Okay. Now, hypothesis testing is not only done for population means, it's just depending on what you're testing, you might need a different distribution. Okay, there's lots of different distributions. There's just so many of them, we didn't really cover a whole bunch of them. So you would just need to find out, okay, what distribution do I need for whatever it is I'm trying to test here. Okay. And that's really all there is to say about this. The only thing we should note, well, I guess one thing we can note here is that a hypothesis test, whoops, the hypothesis test using the t distribution using the t distribution is often called a t-test. Okay. So it'll just be referred to as a t-test. There will be another test later called the f-test that we'll see in chapter 13. So this is just a hypothesis test where you're using the t distribution. In order to do this, we need some assumptions, the same assumptions we need in general to use the student's t distribution. We should have a population that's approximately normally distributed, and we should be dealing with a simple random sample, which just means that the sample is taken completely randomly. Okay. If so, that's a t-test. Whoops. There we go. A hypothesis test these are all here. I'll just make a note up here. These are all for single population mean mu. Okay. A hypothesis test using a normal distribution is often called a z-test. Okay. So this just comes from the fact you're using z-scores, right? In the t-test, you're using the t-scores, z-test, using the z-scores. Okay. If you're doing it with the binomial distribution, I don't think it has a special name. Yeah, it doesn't look like there's one mentioned here. But like I said, we're skipping over those for now. So that's actually everything that's in this chapter is just what we call these tests. Okay. And then which distribution we're using, the same as when we were doing the confidence intervals. Okay. It just depends on that population standard deviation and whether or not we know it. So let's go on to 9.4. This one's called rare events. Sorry, one sec. My writing utensil is not working. All right, sorry about that. Finally got it working again. So let's go on to 9.4 now. So first we're going to look at using the sample to test the null hypothesis. Okay. So this is typically what we're trying to do. We take our sample data and then we use that to test whatever the null hypothesis is. As an example of what that could look like, if we go back to 9.1, one example was we want to test whether the mean GPA of American college students is different from 2.0. So the null hypothesis was that it is 2.0. Okay. So this is all centered around what's called the p-value. Okay, so this is a very important concept in statistics. It is a little bit controversial nowadays. There's been some discussion about moving away from p-values. If that happens, it's not going to be anytime soon. Probably it'll be a slow transition away from them. For now, though, p-values are very commonly used. So, I mean, if you read any like sociology paper detailing or using statistics, you'll probably read about a p-value at some point. Okay. So p-values are sometimes called probability values. Okay. So we use as the title says here, we use the sample data to calculate the probability of getting the test result. Okay. So we take the sample data, we use that to calculate the probability of getting the test result. So like in 9.1, that would be the probability that the mean is 2.0 kind of thing. Okay. This probability is called a p-value. Okay. And now a little bit more of a precise definition of a p-value. The p-value is the probability that if the null hypothesis, H naught, is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. Okay. So let's break this down because it's a little bit confusing here. I'll read it again first. The p-value is the probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from this sample. Okay. So we have our current sample, right? And we're saying, okay, if we duplicate this test, so this is all about duplicating the test. If we have our one sample here. If we took another sample and did the test again, then this is the probability that the results will be the same or more extreme. Okay. So, in other words, we're looking at what's the probability that our results are only due to random chance. Okay. This is where the term statistically significant comes in. We say things are statistically significant if they are under a certain p-value. Because if there's a large p-value, that would say that there's a high chance that our results are only from random chance. Okay. So low p-values means that there's a low chance that our results are only from random chance. In other words, low p-value means there's a low chance that this is just a coincidence, right? Whenever we take a sample, there's always a chance that our results are just a coincidence, right? That, it's just because of something from this sample. And that's usually why we want to take a lot of samples and do the experiment many times. But the p-value gives us a number that says, okay, there's only a 5% chance that this is due to coincidence. Or maybe there's a 50% chance that this is due to coincidence, in which case we don't want to look at these results at all because these aren't good results. So let's look at this next sentence here, which says a large, pretty much what I said, but restated differently using this terminology. A large p-value indicates that we should not reject the null hypothesis. Okay. So if the p-value is very large, say like 50, then that would mean that there is a 50% chance that our results are not just a coincidence. So we should not reject the null hypothesis. Rejecting the null hypothesis means we're accepting the alternative hypothesis, which means we're concluding that we were right about whatever our experiment is testing. If the p-value is large, we can't conclude that we were right because we're saying there's a big chance that this is just due to random chance. In other words, our results are not statistically significant. Okay. We would need a small p-value to determine that something is statistically significant. Okay. All right, let's look at let's look at an example here. Let me get one. Okay, so let's look at example 9.9 from the book. I just copy and pasted it here. And I'll increase that font size. Okay. All right, so we're going to suppose, get a little bigger actually. There we go. So this is example 9.9. So suppose a baker claims that his bread height is more than 15 centimeters on average. Okay. So this is what we're testing. Several of his customers do not believe him. To persuade his customers that he is right, the baker decides to do a hypothesis test. He bakes 10 loaves of bread. the mean height of the sample loaves is 17 centimeters. The baker knows from baking hundreds of loaves of bread that the standard deviation for the height is 0.5 centimeters and the distribution of heights is normal. Okay. So the first thing we always want to do is establish what is our null hypothesis. And from that, we get also what is the alternative hypothesis. Okay. So the null and the alternative. So what we want to test is that the bread is more than 15 centimeters. That's what we want to know, or what we're claiming, rather. And that's going to be the population mean in this case, right? Because it's an average, and it's he's claiming that this is true for all of his bread, which should be the population. So we're claiming that mu is more than 15, and that's in centimeters. Okay, so that's the alternative hypothesis. That's what we are claiming. I can't draw a very good mu. That's a mu. So the null hypothesis is just the opposite of this. It's going to be that mu is less than or equal to 15. Okay. And we're going to do our test using the null hypothesis and decide if we're going to reject it or be unable to reject it. Okay. So let's look at the other information that we're given here. We bake 10 loaves of bread. So 10 is going to be our sample size. Okay. The mean height of the sample loaves is 17. Okay. So that's going to be our X bar. Our sample mean is 17. And from baking hundreds of loaves of bread, we know that the standard deviation is 0.5 centimeters. So we're making the claim that the population standard deviation is 0.5 centimeters. That's why it's going out of its way to specify that this is from baking hundreds of loaves, and it's not just from the sample. Okay. If it was just from the sample, then this would be the sample standard deviation. Then we'd be doing the t-test. Because it's from hundreds of loaves, this is the population standard deviation, and this is this is sigma. And so we're going to be doing a z-test. Okay. So remember that I'm trying to remember what section this was from. Was it chapter 6 where we talked about the X bar, the distribution of X bar? I think it was actually 7. Yeah, right here. Okay. So we're testing for the sample mean. So this is what we're looking at, is this big X bar. So our X bar is normally distributed with the same mean, which is what we're looking for, but notice that the standard deviation is this. Okay. So our standard deviation is sigma divided by the square root of n. So that's the number that we need. Okay. Sigma is this, so sigma over root n is 0.5 divided by 10, which is 0.05. Okay. Sorry. No. It's the square root of 10, not 10. And then this is going to come out to 0.16. Okay. So this is the number we're looking for because we're looking at the it's the keyword here, on average. Okay. This is telling us that we're not just looking at this one sample, we're looking at big X bar, which big X bar was the sample means. Okay. And that's what we're testing for. So we're looking for this. We know this part, we can get it based on this information. So ultimately, we need to find what we're trying to find is this mu x. Okay. So this is the standard deviation we're working with. This is the sample mean. So now let's look at what we should do. Okay. So we want to suppose H naught is true and then see what happens. Okay. If H naught is true, that means that mu is less than or equal to 15. And then we want to see if that is true, is the fact that this time it came out as 17, is that unreasonably large? Okay. So mu is less than or equal to 15. Then is the fact that this sample's mean height is 17 unlikely. Okay. So that's what we're testing here. We're saying, okay, this time we got 17. How unlikely is that if the null hypothesis is true? Okay. Let me see. I think it'd be better if I just copy and pasted this picture here instead of trying to draw it. So let me grab that. Okay, so we want to look at the p-value now. I got the picture, but let me write something down first here. Then the p-value, so this is the bolded sentence from the book here. The p-value is the probability that a sample mean is the same or greater than 17 centimeters when the population mean is 15 centimeters. Okay. So in other words, this is the probability that this would happen again if we replicated this. Okay. And we can calculate this probability just using the normal distribution. See if I can get my picture in here. Did it work? Did. Let me try to put it over here. There we go. There we go. So this is the p-value. So why is everything why is this part of it shaded? Well, what we're looking for, the p-value is equal to the probability that x bar is bigger than or equal to 17. Okay. It's the probability that a sample mean is the same or greater than 17 centimeters when the population mean is 15 centimeters. Okay. As you can see from the picture, it's pretty small. It says right here it's approximately 0, which we can confirm by doing the actual calculation in something like Excel. So our sample mean, or the population mean rather, is 15. If the population mean is 15 and we know that the population standard deviation is 0.16, then what is the probability that this is right here? We can calculate the z-score. Okay. the z-score. We would have 17 minus 15. So it's the number here minus the mean that we're working with, which is 15, divided by 0.16, which would be 2 divided by 0.16 is 12.5, which is extremely high. This is, remember, the z-score tells you how many standard deviations you are away from the mean. This is saying what's the probability that we're 12.5 standard deviations away from the mean, okay? Which, remember, with a normal distribution, almost all of the data, 99.7% of the data is within 3 standard deviations. So this is extremely high, and that's where we're getting the fact that the p-value is almost 0. You're not even going to find this on a table because it's so high. Okay, so this is approximately 0. It's going to be like 0.0000 something, you know. So you would round it to 0. Okay, so what does this mean in terms of the hypothesis test? Okay, we have a very small p-value. This means that it is very unlikely that this is only due to chance. So because the p-value is so small, it is highly unlikely that this is due to chance. When I say this, I mean the fact that it's 17 centimeters. Okay. So, we reject H naught. Okay. Because remember, H naught was this, right? So now we're saying there's sufficient evidence that the alternative hypothesis is true, which is that the mean height for the population is greater than 15 centimeters. The p-value is telling us that the fact that it came out as 17 this time, there's almost a 0% chance that that's just a coincidence. And thus, the fact that it's 17 this time gives us sufficient evidence to say, okay, it is typically more than 15 centimeters. Okay. Now, this was all, the key to all of this was knowing the population standard deviation. Okay, without that, we really couldn't know most of this. So, we're always going to need some form of standard deviation. Usually finding the population standard deviation, though, could be kind of difficult. So if we have instead like the sample standard deviation, then we would do a t-test with it instead, which is pretty much the same thing, except for instead of calculating the z-score here, we would calculate the t-score. Okay. So this is basically an entire hypothesis test right here. So let's do, I mean, I'm kind of jumping the gun here by saying that we reject H naught. So let me just maybe throw this in parentheses because we technically didn't actually look at how we make that decision. Really, with the p-value, we should only conclude this. We need one more condition to be able to actually take that next step. and reject H naught, which we'll talk about in the next section. But first, I would like to do another example of this because I know we kind of went through it slowly. So let's just do another one to hopefully avoid any confusion here. Let me just go ahead and grab this one. Okay. I mean, there's really not anything to write down because they do most of the problem here for us, but let's go ahead and try to interpret it at least. Okay, so this one says a normal distribution has a standard deviation of 1. We want to verify a claim that the mean is greater than 12. A sample of 36 is taken with a sample mean of 12.5. Okay. So it does a lot of it for us here. You can see that they write out the null hypothesis. We want to verify the claim the mean is greater than 12, so that's our alternative hypothesis. And then the null hypothesis is that the mean is less than or equal to 12. Some things it doesn't write down, which we don't really need because they already calculated the p-value. But we have n equals 36 and x bar is 12.5. And we know that sigma is 1. Okay. So we would need, first of all, if they didn't give us the p-value here, we would need sigma divided by root n, which would be 1 over square root of 36, which is 1 over 6. Okay. And you can make that a decimal if you'd like. And then if you just go back to what we did last time, after that, then we try to calculate the p-value, which, like I said, they already did. But the p-value, let's just make sure we get the same thing as them. The p-value is the probability that x bar is greater than 12.5. So that's the, just like this was the sample mean last time, we're using the sample mean again in this 12.5. Okay. And then we'd calculate the z-score. Which we'd have 12.5, the number here, minus the population mean that we're assuming, which is 12, divided by that 1/6. So if you want to put it in a decimal at this point, 1/6 is 0.167. Okay, it's 0.16 repeating, so you got to round it. So we would have 0.5 divided by, I'm just going to put in 1/6 because that'll give us an exact answer of 3 here. Okay. So the z-score is 3. So remember, the z-score is how many standard deviations away you are. So we're saying what's the probability, essentially, that we are more than 3 standard deviations away. Okay. So if you remember the bell curve, this is mu, and then we have mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. So this is what we're looking for, is what's the probability of being in this region. Okay. So not drawn to scale or anything here, but one thing that we found from the empirical rule is the region from here to here, which is the 3 standard deviations, that accounts for 99.7% of the data. So that means outside of that is only 0.3% of the data. So in this part plus this part, you have 0.3% of the data, which means in just one of those, you would have 0.15 0.3 divided by 2. Yeah, 0.15% of the data. Okay, which is almost what the p-value is here. The 99.7 is just an approximation, so that's why it's not exactly the same. So we can just do that just using the empirical rule, or you can go ahead and use the table to find. You would use your 3 and find that on the table. Okay. So we get about the same p-value here. So what is this p-value telling us? It's telling us that there's only a 0.13% chance that this is just a coincidence. So there's pretty good evidence for rejecting the null hypothesis here. There's pretty good evidence that the population mean is greater than 12. Okay. Okay. Like I said, though, we need a little bit more before we can definitively make that statement. So it's actually going to depend on our alpha value a little bit. So let's look at the last section in 9.4 here, which is called decision and conclusion. So this is how do we make our decision and how do we make our conclusion. So the way we decide whether to reject or not reject the null hypothesis is to compare the p-value and the significance level alpha. Okay. I'm saying the significance level alpha because this is the same significance level we saw back in chapter 8 with the confidence interval. I just go back up to that definition as a reminder here. Let's see. Right here. Okay. We called it the at some point we called it the confidence level. Okay. The confidence level was 1 minus alpha. So alpha itself is known as the significance level. You also might remember that same letter over here in the type 1 error, and this is also the same thing. Okay. So we're going to be looking for the probability of the type 1 error. That's the significance level. Okay. Okay. So a preset alpha, preset meaning we determine what it is before we start the experiment, is the probability of a type 1 error. Okay, so why, in this context, why is this coming up? Why are we comparing the p-value to the probability of a type 1 error? Well, let's look back at what the type 1 error was. The type 1 error is the case where we reject H naught, even though H naught was true. The p-value is the basically if there's a high p-value, it means that we should not be rejecting H naught because it's not a coincidence. So they're both kind of looking at the null hypothesis, and um, the idea is that the if alpha if the p-value is bigger than alpha, so if the probability that our results are not a coincidence is higher than the probability of making a type 1 error, then we should not be rejecting the null hypothesis. But if it's the other way around, if our probability that it's not a coincidence is lower than the probability that we're rejecting H naught when we shouldn't, then we can safely reject H naught. Okay. I know that's pretty confusing though, so let me just write out exactly what we're doing here. So we make a decision, okay, to reject or not reject H naught as follows. If alpha is bigger than the p-value, we reject H naught. Okay. And this would mean that we're accepting the alternative hypothesis, and that means that what we were trying to prove is true. So we want the p-value to be less than alpha. So a lot of times if you're reading like a sociology paper, you'll read like our results were statistically significant, and then it'll have in parentheses p-value, or actually it'll just usually write p is less than 0.05. So if they're saying the results are statistically significant, then they're saying, and then they say this, parentheses, p-value is less than 0.05. 0.05 is commonly what alpha is. That's the significance level that we determine before we start. If you remember back when we were doing confidence intervals, we would determine, okay, we want to make a 95% confidence interval, so we're going to let alpha be 0.05. Same idea here. It's the same alpha. So if your p-value comes out to be less than 0.05, then you can say it's statistically significant. Okay. So you'll often see this one in particular when you're reading papers, because 0.05 is a very common choice. Okay. So it just says the book notes here. It's just saying the results of the sample data are significant, statistically significant, and we are saying that there's sufficient evidence to conclude that H naught is incorrect and that the alternative hypothesis may be correct. Okay. Now, on the other hand, if this is the case, okay, so alpha is smaller than the p-value, this typically just means, alpha is typically always pretty small. So this is really just saying that your p-value is very large. So if you set alpha to be 0.05, for example, and you get your p-value to even just be 0.06, this is where you would fail to reject. Okay. So notice that we're never accepting H naught. We're never saying, okay, H naught is definitely true. We're just either rejecting it or we're failing to reject it. Okay. Oops. Sorry about that. So the last point the book notes is what I just said here. Like, we're not actually accepting H naught. We're just failing to reject it, which just means that we're like failing to provide sufficient evidence. Okay. I think a good analogy for this is like if you're a jury and you're determining whether somebody is guilty or not guilty, you're doing what I just said. You're determining if they're guilty or not guilty. You're not saying they are guilty or innocent. Okay. There's a very subtle difference there, which is that you're not necessarily saying we know for sure they didn't do it. You're just saying it seems unlikely. So we're not able to say that they are innocent. Or sorry, we're not able to say that they are guilty. So we're going to call them not guilty. Okay. Okay. So let's see if we can go back up to one of these. Well, like for this one, for example, with the bread one, our p-value was almost 0. So like there's almost no way we're going to get a result different from reject H naught. We would have to have an alpha even smaller than this. And like I said, alpha is typically 0.05. So we don't have to worry about that there. This one, we're definitely going to be rejecting H naught. This one, our p-value is 0.0013, which is definitely smaller than 0.05. Even if you want a 99% confidence level, that's going to be your alpha is going to be 0.01. This p-value is still going to be smaller. So in this case, you're definitely going to be rejecting H naught as well. Okay. So I think the last thing we need to do here now is just put everything together, right? We just need to do like a full hypothesis test. So let's go ahead. That's exactly what section 9.5 is. Okay. Full hypothesis test examples. Okay, so we'll do a couple of these here. One thing it notes is that, alpha should be determined beforehand. Okay. Specifically, you should determine alpha, let me say, before before collecting the data. Okay. If alpha is not given, it is common to assume it is 0.05. Okay. That's probably the most common alpha we'll see. So just basically it's 0.05 unless otherwise stated. Okay. So let's go ahead and look at an example. Just find a good one here. It talks a little bit about one tail in two-tailed tests. Which is just basically talking about the tails on the bell curve again, whether you're using one or two of them. So let me copy and paste an example for you guys here. Okay, let's take a look at this example, which is example 9.14. Okay. Here we go. All right. So Jeffrey, as an 8-year-old, established a mean time of 16.43 seconds for swimming the 25-yard freestyle with a standard deviation of 0.8 seconds. Okay, they're highlighting most of the important stuff here, as you can see. His dad, Frank, thought that Jeffrey could swim the 25-yard freestyle faster using goggles. Frank bought Jeffrey a new pair of expensive goggles, timed Jeffrey for 15 25-yard freestyle swims. For the 15 swims, Jeffrey's mean time was 16 seconds. Frank thought that the goggles helped Jeffrey swim faster than the 16.43 seconds. Conduct a hypothesis test using a preset alpha equals 0.05. Assume that the swim times for the 25-yard freestyle are normal. Okay, so we're given alpha is 0.05, and that's not going to come until the end when we calculate the p-value. All right. What's some other information we get here? Well, our sample, there were 15 swims, so our n is 15, the sample size. The sample mean is 16 seconds. That was the mean of that sample. Okay. The population standard deviation we were given is 0.8. Okay. And then we need to set up the hypothesis test. Okay, so what's our H naught and what's our HA? Well, what we're testing, what his dad, Frank, is testing is that he can do the 25-yard freestyle faster, meaning that our mean is faster than 16.43. Okay, so the mean is greater than 16.43. And the null hypothesis would be the opposite of that, that it's less than or equal to 16.43. Okay. Now, all right. So that's all the information we need. So the first thing we should do is calculate the standard deviation of the means, which is sigma over the square root of n. Okay, so 0.8 divided by the square root of 15. So we get our calculator out. We got 0.8 divided by the square root of 15, and that's approximately 0.21. Okay. We have to round a little bit there. Then, using this, we want to calculate the p-value. Okay. So the p-value is the probability that x bar, should be a little x bar, they kind of blend together, is oops. Yeah. Okay, just wanted to make sure. The probability that it's less than 16. Okay. Because 16 is the sample mean here. So if we were to look at the picture, our population mean is 16.43. So 16 is going to be over here. So we're looking for this value. Okay. The way I drew it, it looks very large, but I'm not trying to scale. So what is that actually? We're looking for the probability that x bar is less than 16 here. Okay. In other words, we're saying, okay, what is the probability that it being 16 here is just a coincidence. Okay. So we need to find the z-score for this. That's going to be 16 minus the 16.43 divided by this 0.21 here. So we're going to get negative 0.43 divided by 0.21, which is negative 2.04. We can say negative 2.05. We don't necessarily need exact values here. Okay. If you remember, sorry, this is saying that it is 2 standard deviations to the left of the mean. Remember, 2 standard deviations accounts for 95% of the data. Okay. So for just half of it, it's going to be about 2.5% of the data, right? Left over, because in the tails left over, there's going to be 5%. So in just one tail, there's going to be about 2.5%. Now, this isn't exactly 2. So we should be a little bit careful here. But if it's going to be, if it's not anywhere close to alpha, then we don't really need to worry about it, right? 2.5%, the probability, so that means the probability that this is true is less than 0.025, right? Because 2 standard deviations would be like, just right here would be 0.05 closer. So this would be even less than that. So you don't need to find an exact number if you don't want to pull out a table or whatever, if you just want to use that empirical rule. Or you just go to the table and you put in the negative 2.05 on that table. And according to the book, you should get 0.0187. Okay. But because we know this is even less than 0.025 and we know this is less than alpha, okay, then we know that the p-value is less than alpha, so we reject H naught. Okay. We reject H naught. H naught was that the mean would be the same or slower. So this means it supports our hypothesis that the population mean is actually larger than 16.43. Okay. Now I think this is an example where it's a little bit surprising because the established oh, sorry, wait, I was thinking about that backwards. No, 16 would be faster than 16.43. I was just thinking it's a lower number. But no, it's faster, so I guess it's not that surprising. So yeah. Let's do one more example here. Okay. I got this one where we're going to be using the t-distribution. Okay. And this is example 9.16 from the book. So statistics students believe that the mean score on the first statistics test is 65. a statistics instructor thinks the mean score is higher than 65. He samples 10 statistics students and obtains the score 65, all that. He performs a hypothesis test using a 5% level of significance. The data are assumed to be from a normal distribution. So immediately alpha is 0.05, right? A lot of this we have to do the heavy lifting on, okay? So we'll need to get out our Excel or whatever it is you would like to use. So let's go ahead and put the data in. We got 65, 65, 70, 67, 66, 63, 63, 68, 72, 71. And from that, we're going to need the sample mean and the sample standard deviation, right? There's no way for us to get the population standard deviation here. So we're going to have to use the sample standard deviation, which is why we're going to be using a t-test, okay? So we go to our formulas here. So we got average for the sample mean, spits out 67. And the standard deviation sample spits out let's call that 3.2. Okay. So we have X bar at 67 and S at 3.2. Okay, we're using S now instead of sigma because it's the sample standard deviation. What else do we need? We need, of course, the null hypothesis and the alternative hypothesis, right? The alternative hypothesis, we're looking at this from the point of view of the statistics instructor. He's trying to prove that the mean score is higher than 65. Okay, so HA is that mu is higher than 65. H naught is that mu is equal to 65. Okay. So notice it's not less than or equal because the students are assuming that it's actually 65. But it's all going to work out the same way. There's not really going to be any difference based on that. Okay. We're assuming the data is from a normal distribution, which we need in order to use the t-test. Okay. And we also have, we also might need n, okay, which is the sample size, and you might notice that there's 10 of them here. So we get n equal to 10. So what are we going to need? We're going to need t. Well, let's go back and think about what we needed for the t distribution, because remember we needed that thing called the degrees of freedom. I think that's an 8.2 here. Yeah. So remember the degrees of freedom for t was n minus 1. So 1 less than the sample size. Okay. And we also typically needed, well, we'll come to that in a second. Okay. So, well, let's just write first of all, the degrees of freedom is equal to 10 minus 1, which is 9. Okay. So we want to calculate the p-value, but the only difference is now we're going to be using the t-score instead of the z-score. Okay. So we're looking for the probability that X bar is higher than 67. Okay. Because that's what the sample mean was. So let's look back here. Hang on one second. Let me look at one thing. Okay, this is what I was looking for here. The formula for the t-score. Okay, so we have X bar minus mu over S over the square root of n. Okay. So the t-score We have X bar, which was, sorry, this should have been X bar, which was 67, minus our assumed mu, which is 65, over S over root n. So 3.2 over the square root of 10. We can just put this in Excel, I guess. So the top there is 2 divided by 3.2 divided by square root of 10. Close all those parentheses. So we get 1.98, let's say. So that's our t-score. So if we wanted to do this with the table, let me get the t-distribution table pulled up. All right, here we go. So we got the t-distribution pulled up. We are looking at 9 because that's our degrees of freedom. And we're looking for 1.98. Okay. You can see we're not going to get it exactly, but it's somewhere between here. It's between 95% and 97.5%. The 95%, that corresponds to our alpha's 5%, right? So the important thing is the side of that that we're on here. If you did want to calculate this exactly using the t-score, you would end up getting 0.0396 according to the book here. You could do that in Excel. Let me see, t-distribution. There you go. T-distribution. I don't think we've ever done that here. Let me think. We would need to do 1 minus whatever we get here. So this is going to be, what are we putting in? We're putting in 1.98. The degrees of freedom is 9. And we can just leave this, I think you can just leave this blank, or you can put true. So that's 0.96, and then we're going to want 1 minus that because that's giving us the left side. That's what it said. So we want 1 minus B16 to get that 0.03953, which is basically what they got here. Okay. So we hadn't done that before, but it's just exactly like how we were doing it with the normal distribution. But if you did want to do it using the table, what's important here is that it is stuck between here. So this would be our alpha, it would be like 5%. This one would be 2.5%. So you can see it's smaller than the 5%, which is what we're looking for when we're making a decision. It's between 5% and 2.5%, we know. So that's all the information we would really need. Either way, we get that the p-value is less than alpha, so we reject H naught. Okay. So I guess what I'm trying to show here is you don't necessarily have to find the exact value. If you can use the table to approximate it, or maybe use the empirical rule to approximate it, because you're only looking for if it's less than 5% or not. So if you can make that call without getting the exact number, then you're good. Otherwise, you can just put it in Excel and find the exact number. Okay. There's lots more examples on this page right here on the chapter 9.5 here. So if you'd like to look at some more of those, I would encourage that. Like I said, this is a very important chapter because, this is how we make decisions. We have to decide whether or not we're going to accept whatever we're testing. This is what we mean when we say something is statistically significant, is that the p-value is less than the alpha. Okay. All right. So that's going to be it for this lecture. So thank you guys for watching, and I will see you on the next one.